Prop 22 says, out of three straight lines, which are equal to three given straight lines, to construct a triangle, thus it's necessary that two of the straight lines taken together in any manner should be greater than the remaining one. So the last part is sort of like a constriction on this setup, and it comes from Prop 20, which was the triangle inequality, which said that in any triangle, the sum of two sides is always greater than the third. So the implication there is that for a triangle to be formed, the triangle inequality has to be satisfied. So that's all that this last piece is saying. Right. And I kind of wanted to do, well, when I was thinking about how to do this video, I thought of doing it in two different ways, because Euclid's proof just uses Prop 3. And Prop 3 is the one that allows us to use basically a non-collapsible compass that says that's okay. And so what I had originally thought was, and using Prop 3, this becomes just like a very quick, straightforward proof. And so what I initially thought was, maybe I'll, instead of using Prop 3, I'll use Prop 2, like 3 different times. Because Prop 2 is the one that Prop 3 is built on, obviously, and it's done by assuming that you have a collapsible compass. And I decided against that, and I'll show you at the end why, because I have the diagram that I made. And it gets pretty messy pretty fast, but using Prop 3, this is sort of an anticlimactic proposition. So let's see, what does Euclid say? He says, first of all, let there be set out a straight line DE, terminating at D, but of infinite length in the direction of E. So just some line that goes on forever, but it starts at point D here. And he says, on this line, DE, let's construct DF, so that DF is equal to A. So here's F, and again, that's just coming from, we can use a non-collapsible compass. So I just used my compass to just translate down DF is equal to A. So let's see here. How should I say? On an infinite line, DE, construct DF such that DF is equal to A. And that is Prop 3 that allows us to do this. And then we're just going to repeat this 2 more times for B and C. So I'll say construct, I guess it'll be FG is maybe the next letter. FG equal to B, and then GH will do, equal to C. So basically just copy all 3 of these lines onto the infinite line, DE, and kind of put them head to tail, tail to head. So here's G, and then lastly H, so that GH is equal to C. Okay, so we've got all of our pieces on here now. And what's next? Just erasing some of these smudges. I'm using a charcoal pencil now, and it's a little smudgier than I'm used to, so it's going to take some getting used to, I think. Okay. Right, so and now that we've made all of this, so the next thing is, with center F and distance FD, let the circle DKL be described. So in our notation, we're just constructing a circle with center F and radius FD. And that just comes from the definitions that say we're allowed to do that. So we don't need to cite a proposition or anything. That's not even a postulate, it's just definition. I suppose it's kind of a postulate, maybe postulate 3, if I'm remembering right. I don't remember now. But previously, Euclid just would cite definition 15 when he was making circles. Okay, so we call this DKL. I'm going to not label the K or the L right now, just because I don't want to clutter things up too much. It makes it a little bit less intuitive. And after we've created that, we construct another circle, but this time with center G and radius GH. So construct G, radius GH. Okay, and I'm just making the semicircles here. You could make the whole circle. Nothing really changes except that on the next step you're going to have two intersection points. There we go. So there's our second circle. And can you guess where it's going? Should be pretty obvious at this point. Well, hopefully. It's alright if it's not obvious. That's not a problem. Alright. So, and Euclid calls this intersection of the two circles, he calls that K. So I'll say, let K be the intersection. I'm running out of room. Okay. And then the claim is that, and I guess I should have said this, but hey, I'm not going to add it in now since it's too late. But we need to connect KF and KG. And the claim is that this is our triangle. There we go. So the claim is that triangle, we'll call it KFG, is the required triangle. And it doesn't matter how obvious it is, we need to prove it. So the proof is nice and quick. So let's see here. By construction, we have A was equal to DF, and DF is equal to FK, because they're radii of the same circle. So A equals FK. FG is equal to B. So B equals FG. And again, that was just by construction. We just said copy B down. And then lastly, same argument for C. C is equal to GH. And GH is equal to GK. So C equals GK. And that's really all that we needed to prove, is that those are the three lines that we were given at the outset. So since this one is a construction proof, it gets a QEF. There. Done. Right. And then the very last thing, like I said, so this is just using proposition 3, I guess 3 times 1, 2, 3 times, and then creating two circles. My initial thought was, if I wanted to make this diagram a little bit more robust, maybe not quite so simple, maybe instead of using prop 3, I'll use prop 2, and here's what that ends up looking like. So up here at the top, this is just like a scratch paper. Up here at the top is the normal construction, basically what we just did. Down here is the construction where you just use prop 2, so it's just circles on circles on circles. And the triangle to be formed is right here, and it's kind of buried in here, but the lines are, here's A, here's B, and here was C. So just making circles and translating them down without using using prop 2, without using prop 3, you just get all of these circles. So anyway, that's prop 22.